In the modern diet, the primary source of metabolic energy comes wrapped in a highly porous, fragile matrix. When we consume heavily refined carbohydrates, we are ingesting a structure that has already been mechanically shattered. The standard clinical heuristic for managing blood sugar relies on a simple mathematical equation. Patients and dietitians calculate the total grams of available carbohydrates in a meal to predict the resulting postprandial glycemic response. This diagram compares the nutritional profiles of two different foods tested in a recent randomized crossover trial by Kanata and colleagues. On the left is standard white wheat bread, and on the right is a bread made with finely milled chickpea flour. Both servings contain exactly 50 grams of available carbohydrates. Chickpeas are complex legumes, whereas refined wheat is a simple grain. Yet the extreme mechanical processing strips away the chickpea's structural advantages. By the time it reaches the oven, its physical matrix is destroyed, equalizing its metabolic impact with the refined wheat. When subjects consumed these breads, researchers measured the incremental area under the curve, or IAUC. The IAUC is a mathematical calculation that quantifies the total rise in blood glucose levels above a baseline over a specific period of time. Despite their different botanical origins, the postprandial glucose IAUC for both the wheat and finely milled chickpea breads mapped virtually perfectly over one another. A gram of carbohydrate on a nutrition label does not dictate how the body will process it. The physical microstructure of the food matrix determines the metabolic outcome. The Kanata trial introduced a third test variable to observe how physical structure influences digestion. They replaced 30% of the refined wheat flour with a different ingredient. Instead of the finely milled powder, this third bread utilized large particle chickpea flour. The granules were milled to a size above 1.45 millimeters, compared to the sub-210 micrometer dust of standard flour. This relies on a strict geometric principle. Larger particles possess a significantly lower specific surface area to volume ratio. Because the particles are physically larger, thousands of individual plant cells remain completely unbroken by the milling process. This diagram illustrates the structural difference. On the left is the thin-walled wheat cell, easily shattered during milling. On the right is the thick, intact chickpea cotyledon cell. Its walls are highly reinforced by a dense network of complex carbohydrates, specifically pectin and xyloglucans. These dense legume walls are uniquely resilient. Even under severe hydrothermal processing and high baking temperatures, the cells remain completely intact. This creates a phenomenon known as steric hindrance. Steric hindrance is the prevention of a chemical reaction caused by the physical arrangement of atoms or molecules blocking access to a target. Here, digestive alpha amylase enzymes easily flood the shattered wheat cells, but physically bounce off the thick, intact walls of the chickpea cotyledon, leaving the encapsulated starch untouched. The degree of mechanical milling dictates the accessibility of the energy inside. By leaving the physical barrier intact, the food's structure overrides the raw carbohydrate count listed on its nutritional label. This graph compares the postprandial glucose curves. When subjects consumed the large particle chickpea bread, the blood sugar curve was distinctly flatter than the finely milled control. The clinical data showed a 26% reduction in the glucose incremental area under the curve. Protecting the starch produced a secondary endocrinological outcome deeper in the gut. This graph shows total plasma GLP-1 concentration, an incretin hormone regulating appetite. Following ingestion of the large particle bread, GLP-1 secretion was 2.3 times higher compared to the flatlined control. Protected by intact cell walls, the starch bypassed rapid absorption in the duodenum. Instead, it traveled intact deep into the distal colon. This triggers the ileal brake. The ileal brake is a feedback mechanism in the digestive tract, where the presence of unabsorbed nutrients in the lower intestine slows down gastric emptying and upper gastrointestinal transit. Nutrient-sensing L cells located in this distal gut detect the late-arriving carbohydrates and secrete GLP-1 to put the brakes on digestion. Physically protecting starches from early digestion shifts the body's metabolic response. Instead of a reactive, insulin-heavy spike, the body transitions into a sustained, incretin-driven homeostasis. Not all carbohydrates have the benefit of thick cotyledon cell walls. Foods like white rice, potatoes, or extruded pasta lack this inherent physical armor. When raw starches are exposed to boiling water, they undergo gelatinization.
The granules absorb water, swell rapidly, and burst open, dissolving into a translucent mass. This diagram shows the molecular state of gelatinized starch. The highly organized structure of the raw grain is destroyed, leaving loose, disorganized chains of amylose and amylopectin. In this state, the broken intermolecular bonds are highly susceptible to rapid enzymatic cleavage. A starch's mechanical milling history is only half of the equation. Its thermal history provides a second opportunity to engineer the food matrix. We manipulate this through retrogradation. As gelatinized starches cool, the disrupted amylose and amylopectin chains realign into a rigid, crystalline structure. This requires sustained exposure to temperatures below 40 degrees Fahrenheit. Over 12 to 24 hours, the loose chains rapidly interlock into a dense grid. This recrystallization converts rapidly digestible starch into resistant starch. The rigid molecular bonds act like intact plant cell walls. They physically block digestive enzymes in the small intestine from absorbing glucose, forcing the starch to travel further down the digestive tract for colonic fermentation. Through thermal retrogradation, we can engineer a rigid molecular barrier against rapid blood sugar spikes, even when a physical cellular barrier is completely absent. The final variable in food matrix engineering relies on chemistry. We can deliberately introduce specific active botanical compounds that inhibit digestive kinetics. Certain soluble fibers possess unique mechanical properties. The seeds of the fenugreek plant provide a clear clinical example. Inside the intestinal lumen, hydrated fenugreek soluble fibers expand and dissolve into a thick, highly viscous web-like gel. This gel acts as a physical net. It actively traps free-floating glucose molecules, severely delaying their diffusion across the intestinal wall and into the bloodstream. While fibers act as a barrier inside the intestinal lumen, other compounds target cellular sensitivity directly. Black cumin contains highly active phytochemicals. The primary active compound in black cumin is thymoquinone. It directly targets the insulin-producing beta cells in the pancreas, reducing oxidative stress. This potent phytochemical reduces inflammation, improves pancreatic function, and lowers fasting glucose levels. These exogenous phytochemicals serve as active chemical barriers. By adding them to a meal, they functionally upgrade the glycemic profile of the entire digestive process. We return to the initial paradox. 50 grams of refined wheat and 50 grams of finely milled chickpeas yielded the exact same blood sugar spike, because their internal structural matrix had been completely identicalized by extreme processing. Carbohydrate counting must be viewed as an incomplete baseline. It is a measurement of potential energy, not a comprehensive clinical strategy for controlling digestion. True glycemic engineering relies on a unified framework of 3 pillars. First, manipulating the physical barrier through minimal milling for cellular encapsulation. Second, manipulating the molecular barrier through thermal history, driving polymer recrystallization. Third, manipulating the biochemical environment using targeted phytochemicals and viscous fibers. By mastering the microstructure, the thermal history, and the chemistry of the food matrix, clinicians and patients can move beyond simple carbohydrate restriction. We can leverage the body's own incretin pathways to achieve rigorous, sustainable metabolic homeostasis.